How do you spell that? Yeah. All right. Hi, everybody. We're going to get started. Sorry for the delay. I guess I'm talking today, so Rowi's going to introduce me.
Okay. Hi, everyone. Sorry for the delay. Today we have Ellis, who's going to talk about rounded message optimal distributed graph algorithms.
Okay. Thanks, Rowi. Is it running? Okay. Okay. So, as Rowi said, I'm going to be talking to you all about rounded message optimal distributed graph algorithms. So this is joint work with my advisor, Bernard Heupler, and David Weitz, who's another grad student here in CSD, waving his hand. So distributed graph algorithms, what are those? I wanted to just sort of start by giving everybody sort of the general shtick of distributed graph algorithms. So in standard complexity and algorithms, when we think about like the model of computations that we use, these are usually sort of a centralized model. Like they have all of the input in front of them. They're supposed to perform some computation on that input, and they provide some output. So distributed graph algorithms sort of deal with a model of computations that's decentralized in some sense. In particular, instead of having a single computer, we have, say, a collection of computers. And this collection of computers is able to communicate over some network. And like in the centralized setting, they're supposed to do something like, say, compute a minimum spanning tree. So because our model of computation is decentralized in this setting, every computer in this network has sort of a myopic picture of what's going on. So if I'm this computer at the center, maybe I only know the edge weights of those edges that are actually incident to me. And I'm supposed to then trade some messages with my neighbors. They perform some computation. They might send me some messages back. And based off of this repeated exchange of messages, I'm supposed to like compute the MST. So I guess because in the centralized, or any computation that a single computer is performing itself, given all of the messages it's received, is actually just a centralized computation. So in general, in distributed graph algorithms, we think of each of these nodes as being sort of very powerful. Every computer here has sort of unbounded computation. And then the only thing we think about optimizing in distributed graph algorithms is like the total amount of communication that we perform. So like very broadly speaking, this is like what distributed graph algorithms are about and like the metrics that they hope to optimize for. So there are a lot of ways you could actually more formally ground out this shtick that I just gave you all. So people have proposed a lot of different like distributed models that capture different aspects of what's difficult about distributed computing. I'm just going to throw a bunch on the board very quickly. So you have like the CONGEST model, the SINR model, the radio network model, which is actually what Goran talked about 2 weeks ago at Theory Lunch, the LOCO model, the congested clique model. And the point here is just that depending on how exactly you formalize what it means to do computation in distributed sense, you might end up with like a slightly different model. So for the remainder of this talk, I'm just going to be talking about the CONGEST model. And this is meant to sort of capture what distributed computation looks like if you're performing computation on sort of a wired network, but where there's some sort of bandwidth limitation between nodes. So that's what we'll be talking about for the rest of this talk. So let's just dive into what I actually mean by the CONGEST model. So the CONGEST model formalizes our network as just some graph G, where we think of every vertex in this graph as some computer in our network. At the very beginning of our computation, every node is going to be given some sort of private input. So at a bare minimum, this is going to include some sort of like unique identifier for every node that each of the nodes knows. So maybe they're identified in this way. If we're doing things like MST, maybe this will also include like edge weights or something like that. But hopefully more on that later if I can cram this talk down into 45 minutes. So nodes are then going to communicate in synchronous rounds. And in each of these rounds, nodes are allowed to send messages to their neighbors in the network. So it's worth noting that these messages, in any given round, a vertex doesn't necessarily have to send the same messages to every neighbor in the network. So if I'm a particular vertex in a particular round, I can send different messages to each of my neighbors. So the first round, some nodes might send some messages. The second round, some nodes might send some messages, and so on and so forth. So why is this called the CONGEST model? I alluded to sort of bandwidth constraints. What does that actually formally mean? Well, all we're saying here is just that these messages that nodes send to their neighbors have to be of size order log n bits. So you're not allowed to send your neighbor like every possible like action you might ever take given all of the possible private inputs, like you can only send some sort of limited amount of information to every neighbor. Okay. So like in distributed graph algorithms in general, every node is going to have unbounded computation. And then lastly, the sense of like an algorithm in this like distributed model of computation is just like this thing that we install on every node that takes the node's private input. It takes the node's round that it's currently in and it's taking the messages that it's received from its neighbors. And it just tells it what messages to broadcast in every round. So is anybody not clear on the model or any questions about this model? Because this is important. Okay. Cool. So at this point, you might be saying like, OK, distributed graph algorithms are all about minimizing communication. Great. We've like formalized our model. But it's like not actually clear what communication is here. So we have sort of these two notions of communication. In the CONGEST model, we have like the total number of messages that say all nodes send over all rounds. But we also have like the total number of synchronous rounds you use to communicate. So as a first like knee-jerk reaction to this, you might say, well, you know, maybe like messages and rounds are always like basically interchangeable. Like maybe there isn't any sort of interesting trade-off at play between these two things because, well, maybe you can always bound the messages in terms of the number of rounds and vice versa. And so you might just want to optimize for one, get the other for free. So it's not a very like hard observation to see that the total number of messages that any algorithm sends is always going to be upper bounded by delta, where delta is the max degree of the network, times n, times the total number of rounds. Can somebody tell me why? Anybody? Nama? Yeah. OK. So what Nama said is, in any given round, any node can send at most delta messages. We have n nodes that can do that in any round, so the total number of messages is going to be delta n.
So why big O?
Yeah, I guess you don't really need the big O. That could have just been less than or equal to. But I'm not sure how to do those in Keynote, so. OK, that's a joke. I do know how to do this. OK. So it's actually not that hard to demonstrate or to provide examples where it's clear how you can just optimize for the number of messages at the expense of the total number of rounds you use, or vice versa. So it's actually not the case that these things are always roughly interchangeable. And I can just give you all such an example right now. So suppose that our algorithmic task was we wanted to compute the minimum ID of our network. So here's our network. The smallest ID here is 10 at that node. And at the end of running our like algorithm, we would like every node to sort of announce or be able to announce that like, yes, the minimum ID is 10. OK, so I'll give you all both a round efficient and a message efficient algorithm here. So the round efficient algorithm is actually very straightforward. So all we're going to do is have every node broadcast the smallest ID it's heard in every round, where in the first round, the smallest ID that a node has heard is its own ID. So just in colors, what does that look like? So at the very beginning, every node thinks its own ID is the smallest ID. Every node will then just broadcast what it thinks the smallest ID is to all of its neighbors. Every node updates. So these neighbors of 10 will now think the smallest ID is 10. These neighbors of 12 will now think the smallest ID is 12. They'll do this again. And now every node in the network correctly knows that the smallest ID is 10. So this took only 2 rounds for us. I guess an aside, that's pretty small and up there. But notation I'm going to be using for the rest of the talk. So D is going to be the diameter of our network, where diameter is just the longest, shortest path between any 2 nodes. Delta will be the max degree, n is the number of nodes, m is the number of edges, and tildes are going to hide polylogarithmic factors. So if you think about the round complexity of this algorithm, it'll take something like order D rounds, where D is the diameter of the network. Yeah, and again, you could just write D if you wanted to. So really, it's going to be radius many rounds. But so the order is, I guess, correct here. So why is this? Well, if you think about like the node that actually has the smallest ID, that information sort of travels 1 hop in each round. So after D many hops, every node will have heard that information. But if you think about the total number of messages, like this is sort of bad in some sense. It'll be something like delta n times D, because in every round, every node is going to send up to delta messages. We have n nodes, and we have d rounds. Okay, so does somebody want to like propose an idea for something that's, say, message efficient but not very round efficient? And I guess as a hint / clarification, you can just assume that the smallest ID is no smaller than 0, let's say. So I'll let you all think about that for like 15 seconds. Okay, yeah, Greg, you almost raised your hand, so
yeah,
you get to go.
Could you broadcast with like probability 1 over your ID?
Oh, I don't think so. Let's say deterministic algorithm.
Okay.
Yeah, Rush.
So you divide up the rounds into sequences of delta rounds, or I'm sorry, d rounds.
Yes.
And then so everyone, the first d rounds has value 0, they broadcast, and then
Yes.
1 and 2.
Okay.
And then so whoever has the first one, everyone will get it before anyone else gets
Yeah.
it.
Okay, perfect. So the idea here that Raj just described is we're going to try and have the network sort of check in lockstep. Is the minimum ID 1? Is the minimum ID 2? Is the minimum ID 3? And so forth. And for each of these iterations, like when we're checking if the minimum ID is a particular value, we're just going to take diameter many rounds to allow the network to do this. And what nodes will do here is if their minimum ID is actually the value that you're checking for, they'll broadcast that, like, yes, somebody in the network has this minimum ID. And if during the D rounds you're using for any one of these particular IDs, you get a message from somebody, you know that somebody in the network has that minimum ID. So then you'll tell your neighbors. So, and it's maybe easier to see in pictures. So what does that look like? So for the diameter of this network is like 2. So for the first 2 rounds, every node's going to be thinking to itself, oh, maybe the minimum ID is 1. Let me check that. For the next 2 rounds, every node's going to be doing the same thing except for an ID of 2. And they'll keep doing this for many, many rounds all the way up until they actually get to the minimum ID. So once we get to 10, the network is trying to sort of check if the smallest ID is 10. This node up here actually has a minimum ID of 10. So it'll go like, ah, yes, my minimum ID is 10. Let me tell my neighbors. It'll tell its neighbors. They'll have heard that some node in the network has a minimum ID of 10. They'll tell their neighbors. And now at the very end of this, everybody will know that the minimum ID is actually 10. Yeah?
In order for this to work, doesn't every node need to know the diameter of the graph?
Yeah, that's a good question. So Charlie asked, in order for this to work, doesn't every node need to know the diameter of the graph? That's exactly right for us. I guess in general in distributed graph algorithms, you can sort of play these doubling tricks where you sort of guess these parameters. And if you can efficiently verify that like your algorithm failed, you can always like double your parameter and check again. Let's just pretend for this toy example that everyone knows the diameter of the network. Okay, so let's think about like the complexity of this. Well, we're taking d rounds for each of these iterations. And we're going to keep doing this all the way up until we get to the smallest ID. So our round complexity is going to be d times the minimum ID. And in general, in distributed graph algorithms, you think of IDs as being like poly n. So this is potentially like poly n worse multiplicatively than what we got before. But our message complexity is very good. So we're basically only using the number of edges, messages total in this network, just because every node is going to broadcast at most once. So every edge gets used at most twice. Okay. So it doesn't actually like take that much work to see that this round complexity and this message complexity are optimal for this particular problem. The order d rounds is just because information has to travel at least like the diameter of the network, many hops. The message complexity is like slightly nuanced and a little bit more involved, but just like take my word for it that this is optimal. And I guess the fact that these 2 complexities are optimal tell you that the other complexities are suboptimal. So what did we just do? We showed that it's not very hard to come up with examples where we can perfectly optimize for the round complexity, or we can perfectly optimize for the message complexity, but it's not totally clear how we might optimize for both of these things. Okay? So very broadly speaking, the work that I'm presenting today is sort of interested in understanding what sort of trade-offs are there at play between rounds and messages in these distributed graph algorithms, if any. So the way that we understand this is, or the way that we kind of investigate this is we provide algorithms for certain distributed tasks for these problems. Yeah, Danny.
What would happen if on the left example, the round one, You could optimize it by like not sending the same message again.
Yeah, so,
Like if you had a 10 there, then you wouldn't keep telling your neighbors 10.
yeah, exactly.
10, 10.
So you can, so if you wanted to like actually construct like a bad adversarial example, well, okay, let me just repeat the question. So the question was like, well, if my minimum ID hasn't changed since the last round, why would I like rebroadcast this minimum ID again? So you can, if you think about like a path where everybody has ascending IDs, there are nodes that essentially have to broadcast every round no matter what, like on average. So you can still construct examples where you get a bad message complexity for this. But yeah, for this particular example, you could maybe improve the message complexity by like doing something like that. Okay, good. So, okay, we're going to give algorithms for a number of distributed problems. We solve some sort of distributed version of minimum spanning tree. And this is in d plus root n rounds. So notice that this is a theta. So this is actually the optimal number of rounds. D plus root n is sort of a common lower bound to distributed graph algorithms. We also solve it in theta of m messages, which is optimal. So you might just be starting to think like, well, maybe there's not really a trade-off at play here. We do the same thing for some version of like shortest paths. So it's really approximate shortest paths, and I'm hiding like the poly 1 over epsilons and the approximation factors there. The same thing for approximate and cut. And the way that we get all of these results is we just we improve bounds for a particular primitive that I'm going to call partwise aggregation. In particular, we get an optimal d plus root n rounds for partwise aggregation and m messages for partwise aggregation. So is this simultaneous rounds and messages? Yes, this is simultaneous rounds and messages. So this is a single algorithm for each of these problems that simultaneously gets both of these.
So the lower bound is for just the individual things?
Is the lower bound just for individual algorithms, or what do you mean?
You say for MST, the message lower bound is m.
Yeah.
That's for an algorithm using any number of rounds?
Yes. So the lower bound of m is for an algorithm using any number of rounds. Okay. So just some like minor asides here.
Ellis?
Yeah.
So is the root n also essential?
Yes. I'll give lower bounds in a second, but yeah. So MST, the algorithms for MST and partwise aggregation are deterministic, which is something that people sometimes like in distributed graph algorithms. I guess all of our algorithms also satisfy this nice property that all of these round complexities are actually just order D for certain nice families of graphs. So if your graph is like planar or genus-bounded or treewidth-bounded or pathwidth-bounded, without actually knowing that your graph satisfies these properties, all these algorithms have like a much better runtime on these particular families of graphs. Okay, so like, I guess the main takeaway from like these results, given sort of the mission statement of this work, is that there isn't really any sort of like round or message trade-off for these problems. So you can give an algorithm that simultaneously optimizes for both of these things. And that's kind of like the crux of what we're like doing here. Okay, so I want to just like quickly contextualize our work before getting into maybe some of the technical content, depending on how much time we have. So people have actually been studying like MST and these other distributed graph algorithm problems for like several decades. So in terms of lower bounds for MST, the lower bound of m messages was shown back in 1987. And then about a decade later, David Peleg and some other people showed that you need at least d plus root n rounds. And seeing this d, again, is sort of trivial because information has to travel at least diameter many hops. The root n comes from sort of a nice communication complexity lower bound that uses like set disjointness. If you don't know what that is, it's not important for this talk. So people have been studying algorithms for this problem for even longer. So the first of these was given back in 1983. And the thing to notice here is that like even back in 1983, people were giving algorithms that had basically the optimal message complexity. So the message complexity here is m plus n log n, but basically m. And the lower bound we have is m. But the round complexities were like very far from optimal. So the round complexity here is just n. And we're shooting for something more like d plus root n. A couple of years later, somebody managed to shave a log n from this round complexity, but still the message complexity, or still the round complexity was very far from the lower bounds that we knew. Or that we know now, I guess. I guess at the time they didn't know this lower bound. So Another decade later, somebody gave a round complexity that basically looked like the round complexity lower bound. So this is an optimal round complexity. But on the other hand, their message complexity is like potentially very far off of the message complexity we're shooting for. They have like an order m plus n to the 3/2 message complexity. And again, we're shooting for something like m. So at this point, it seems like the toy example I gave before maybe like had some fundamental truth hanging around in it. Because like people were able to give algorithms that perfectly optimized for message complexity or that perfectly optimized for round complexity up to polylogs. But nobody was able to really give something that did both at the same time. So you might think at this point that, like, yeah, maybe there's some sort of trade-off, and we can get one without getting the other. So,
is it easy to get D plus root n individually?
Is it easy to get D plus root n? No. Well, yeah, that'll be no, I guess. We'll hopefully have time to see how you can get that later in this talk. OK, so actually just last year, Gopal Pandurangan at Fox gave a paper that hit both of these complexities at the same time with a single algorithm. So this is kind of exciting because like this sort of capped off decades worth of work where we weren't sure if you could get both an optimal round and an optimal message complexity. On the other hand, this paper used randomization, and like in TCS, this is sort of something that we like to get away without using if we could. So just last year at PODC, which is kind of the main distributed conference, Michael Elkin gave a paper that also got simultaneous round and message optimality for MST, but used determinism. And for this, Michael Elkin won best paper at PODC last year. So this is like a problem that people have been excited about for some time, and these are sort of exciting results in this space. So I don't want to spend too much time on these other two problems that we look at, like this min-cut problem, this shortest paths problem. I guess the only real thing to note here is that we know how to get the optimal D plus root n round complexities, but we don't really have algorithms that optimize for the message complexity. So these both use like D times n messages, which again is far off of the m we're shooting for. And neither of these algorithms even actually like try to optimize for messages whatsoever. Okay, so I just want to like quickly throw our results back up on the board for a second and point out how this like fits into the larger context here. So basically, no deterministic algorithms for partwise aggregation were known that got both of these message complexities. No message efficient algorithms were known for these shortest paths or min-cut problems. And no simultaneously message efficient and round efficient algorithms were known that had this nice property that for certain restricted families of graphs, you get order diameter round complexities. OK. So for the rest of the talk, I'm just going to be talking about MST and how we might solve MST given a solution for some primitive partwise aggregation that I'll describe more later. Does anyone have any questions before I move on? OK, cool. So in a little bit more detail, the way this is going to look is I'll tell you all what I actually mean by solving MST in a distributed setting, because it's not totally clear what that means. I'm going to talk about how this classic algorithm for MST, Boruvka's algorithm, shows that if you want to solve MST in a distributed setting, you may as well just solve this primitive that I'll talk more about later called partwise aggregation. And so the rest of the talk will just be about how one might hope to solve this primitive partwise aggregation. And we'll start with something naive, then we'll move to something that uses some so-called like shortcuts. And this second idea will get us good round complexity, but not good message complexity. And at the very end, I'll sort of sketch how you might optimize shortcuts to get both good round and message complexities. OK. So let me just quickly define what it means to solve MST in a distributed setting here. So given some graph where every edge has some weight, the minimum spanning tree is just some spanning tree that has minimum total cost, where the cost is just the sum of the cost of its edges. When we're doing this in a distributed setting, we imagine that in addition to their IDs, every node is also going to get the edge weights of its incident edges. So if I'm a node, I don't necessarily learn the edge weights of the entire graph. I don't even know the structure of the entire graph at the very beginning, but I know like the cost of the edges that are just incident to me. And then in a similar vein, we think of the problem as being solved when every node knows which of its incident edges are actually in the minimum spanning tree. So for instance, if I'm this node at the center, at the end of the computation, I'm supposed to know that these two edges are in the MST and these two edges are not in the MST. But I don't actually have to know anything about the structure of the MST in the entire graph. OK, cool. So that's like distributed MST. I want to quickly talk about Boruvka's algorithm, which is a centralized algorithm for MST. This is like 100 years old. So it's been around for a while. So how does Boruvka's algorithm work? So given some graph, I'm not going to draw the edges here just because it'll start to look cluttered. Boruvka's algorithm will start with some singleton partition. So every vertex is just sort of stuck into its own part. It'll have log-n iterations where it gradually coarsens this partition. So the way it coarsens the partition is every part is just going to pick the smallest edge, which is leaving it. Then we're just going to sort of combine parts along the edges that were chosen. And then lastly, any edge that was picked at any point over the course of this algorithm will be in our MST. And there's some like awkward tie-breaking stuff here going on that I don't want to talk about, so don't ask me that question. So, okay, what does this look like in pictures? So in the first iteration, we have the singleton partition. Every part's going to pick the smallest edge, which is exiting it. We sort of get these connected components. So we have this connected component, we have this connected component, we have that connected component. And then we'll just sort of merge down our connected components into their own parts. And then again, we'll pick the smallest edge. And now everything will get merged down into a single part. OK, so that's Boruvka's algorithm. And then at the very end, sorry, any of the edges that were ever picked by our algorithm are like in our MST. So it's like this has been around for like 100 years. It's well known to be correct. I don't want to prove that it's correct for you, but just know that if we could somehow effectively simulate this in CONGEST, then we could solve MST. Any questions about Boruvka's algorithm before I go on? OK, cool. So like, we'd like to think about how can we actually simulate this algorithm in CONGEST. Because if we could run this algorithm, then we could solve MST, which is sort of what we're trying to do. And if we think back to a single iteration, if I'm one of these nodes that are actually incident to the smallest edge leaving my part, I'm sort of happy in a sense. Like, if I'm this node, the smallest edge leaving my part is actually just the smallest edge incident to me leaving my part. And I know all the edges that are incident to me at the very beginning. But on the other hand, like, every other vertex has some smallest edge leaving the part. So they don't know like, if they're supposed to like, merge with like, their neighbors across in the other parts. Or what? So we need to sort of like coordinate parts to have like every node in the part learn if it's incident to the actual true minimum edge. So I'm going to describe how we can simulate Boruvka's algorithm. So distributed algorithms are a little bit awkward to describe. I'm just going to do it from the perspective of a single vertex. So the first thing a vertex is going to do is it's just going to sort of mark all of its neighbors as being in different parts. So this is sort of the analogous step to starting with the singleton partition. Again, we're just going to have log-n iterations where we gradually sort of coarsen these parts. In each of these iterations, nodes in V's part will all sort of come to a consensus as to what the minimum edge is leaving their part. And then what V will do, if it's incident to this edge E, then it will think of its neighbor along that edge as being in the same part as it. So it's sort of locally storing which of my neighbors are in the same part as me. This is like a non-trivial step, but we'll get to that. And then at the very end, we will just, or the vertex V will just return as the edges in the MST any of those edges that were incident to it. OK. So like, if you stare at this for a second, you'll start to realize that basically every step of this algorithm is totally trivial in terms of rounded message complexities. So like none of these steps require any rounds or messages, and none of these steps require any rounds or messages. So really the only thing you have to think about solving is this step right here. How can we get nodes in a single part to agree on the minimum edge leaving that part? So all partwise aggregation, this primitive that I've been going on and on about, is just some sort of generalization of that problem. OK? So what is partwise aggregation? As input, we have some sort of partition of our graph. Now, in this partition of our graph, every vertex has some value associated with it. And the goal, like the problem of partwise aggregation is solved, is once we compute some function of all of the values in each part and distribute the result to corresponding parts. So it's kind of hard to hear in words, easier to see in pictures. So what we'd like to do is sort of like gather up all of the values for each part, apply our function to each of these things. We'd get back a single value. And then we'd like to redistribute this value to vertices according to like which part they're in. And just some minor technicalities, we imagine that this graph partition, all the parts in this graph partition are connected in the underlying communication graph. And sort of all of the values of interest that we have are of size log-n bits. So the values that we start with are log-n bits. This function takes in things of size log-n bits and spits out results of log-n bits. And I guess for the rest of the talk, I'm just going to assume that this function is min just because it makes it easier to like illustrate things concretely. OK. So now if you start to like stare at this orange box that we'd like to somehow solve when we were simulating Boruvka's algorithm, you realize that this is just an instance of partwise aggregation. In particular, every vertex's value is just the minimum edge incident to it that exits its part. And the function that we're interested in here is the minimum function. So stepping back to where we were in our simulation, the point here is just that this is the only thing that costs any rounds or messages. We repeat it log n times. This is just partwise aggregation. So we can make the observation that if we could solve partwise aggregation in R rounds with m messages, then we could solve MST in basically the same bounds, up to log n factors. So it's sufficient for us to just sort of think about this primitive partwise aggregation. That's what we're going to do for the rest of the talk. So I told you all what I actually mean by solving MST in a distributed setting. I told you all how Boruvka's algorithm shows that if you want to solve MST in a distributed setting, you may as well just solve partwise aggregation. So I'm going to step through some partwise aggregation proposed algorithms now. OK, so let's like first talk about this naive idea. So if you think back to earlier in the talk, we gave an algorithm that was basically solving partwise aggregation. Like we gave this like round efficient algorithm where everyone just broadcasted their minimum ID. And this is basically exactly what we're trying to do on each part in partwise aggregation. So our naive idea is just to sort of take this algorithm, run it on every single part, and instead of broadcasting the minimum ID, we'll broadcast like the minimum value that we're trying to solve this problem for. So we already said that this has a round complexity of order D. You know, message complexity is not great, but maybe we can step in later and optimize that. So what this tells us is we basically just solve partwise aggregation order D rounds. And if you remember back to the results slide, the lower bound here was D plus root n. So we're beating the lower bound, so that's like exciting for us, yay. Does anyone see what's wrong with this proof? Yeah, Pedro.
You don't know the diameter of your part?
OK, so you might not know the diameter of the part. But let's say like you do know the diameter of your part. Even then, this is like not good.
So is the diameter of the part the same as the diameter of the graph?
Yeah, exactly. So you don't necessarily know that the diameter of the parts are the same as the graph. So like this order D in the original algorithm was the diameter of the network. We're now running this on each individual part. So we're getting an order D round partwise aggregation solution where D is the diameter of, say, the largest diameter part, not the largest, or not the original graph. So you might say like, oh, well, maybe this isn't actually an issue. Maybe the diameter of a part is always roughly the diameter of the graph. Here's an example where that's not the case. So suppose we have about n nodes at the bottom. They just have ascending edge weights connecting them. So 1, 2, 3. They have some really expensive edge weights connecting them to some more central node. In the first round of simulating Boruvka's algorithm, nodes are going to pick these edges. You merge your parts. And now all of a sudden, we have this really big part at the bottom. It has like diameter n. But the diameter of our original graph is just 2, because every node can go through this central node and hop to any other node. So what does this tell us? Well, we got an order D round partwise aggregation solution, where D is the diameter of a part. But like in the worst case, the diameter of a part can be up to n, which is kind of like the worst case for diameter. So OK, this is the naive idea. It's like not going to work very well. Does anyone have any questions about it? No? OK. So if you start to like stare at this like particular bad example for a second, you might say like, OK, I have this really large part, or this one part with very large diameter. And it's kind of silly for me to try and communicate only along edges in my part. Like I can't ever hope to communicate competitively with the actual lower bounds if I only use edges inside of my part. But if I'm like this vertex over here, and I want to talk to that vertex, it's like really easy for me. I just make 2 hops. I like send information to that one central vertex, and then it sends information back down. So we can sort of make this observation that like maybe if we like let parts use other parts' edges or edges between parts in some sort of principled fashion, we can somehow expedite communication within parts. So this idea is actually going to bring us to my next point, or the next way we're going to hopefully try and solve partwise aggregation, which is this idea of like shortcuts. So we'd like to sort of take shortcuts outside of our part to speed up communication within our parts. So I'm just going to formally describe for you all what I actually mean by a shortcut. So we're going to be talking about a certain sort of restricted family of shortcuts. These are T-restricted shortcuts, where T is some tree. So given some graph partition, all a tree-restricted shortcut is it's some rooted BFS tree. So this is a spanning tree of my graph. It has some root. So like every edge is pointed to the root up there. And because it's a BFS tree, it has diameter roughly order D, where D is the diameter of the original graph. So in addition to actually giving us this BFS tree, we're going to sort of tell every part what edges they're allowed to use. So we're going to specify for each edge which are the parts that can sort of use this as a shortcut to communicate within their part. So for example, this part 1 down here is allowed to use this edge, this edge, this edge, and this edge. This edge up here can be used by parts 1, 3, and 4, and so forth. Okay? So now there are kind of two parameters of interest for us here when we're thinking of shortcuts. The first of these is congestion. And this is just which edge is being used by the largest number of parts. So it's just the maximum over every edge of the number of parts using that edge. So for our particular example, congestion will just be 3 because this one edge is being used by 3 parts and every other edge is being used by 3 or fewer parts. The other parameter, which is a little bit more nuanced, is what's called the block parameter. So I'll just define what the blocks are of a part for you. These are sort of like the connected components you get if you look at a part, or you look at all the edges assigned to a part and you take the connected components. So for example, for part 1, we've assigned to it these purple edges. So these edges and these edges. And if you look at this, you sort of have 2 connected components here. So we have this connected component and we have this connected component. Both of these correspond to subtrees of our original tree-restricted shortcut. So these are just the blocks of part 1. Okay? Is anyone not clear on what the blocks are? Okay, good. So all the block parameter then is just look at every part, look at its number of blocks, and take the maximum number of blocks over all parts. So for our example, the block parameter will be 2 because part 1 has 2 blocks. And if you look at every other part, it'll have 2 or fewer blocks. Okay, so like we have these 2 parameters that like give us some sort of quantification, hopefully, of how good shortcuts are, like how much shortcuts can speed up communication. And so what I'm going to talk about now is like how can you actually come up with good partwise aggregation solutions as a function of these parameters. Okay? So the first lemma that I'm going to very sketchily prove for you all is that if I have a shortcut with diameter D and congestion C, then I can aggregate on my blocks in time, or sorry, if I have a graph with diameter D, but my shortcut has congestion C, then I can aggregate on my blocks in time D plus C, or rounds D plus C. And what I just mean by aggregating on blocks is like every vertex in a block has some value associated with it. I can sort of gather these values up, apply my function, which we're just thinking of as min, and then redistribute the values to the corresponding nodes. Okay, here's my like very sketchy proof sketch, and just the algorithm here is important for what I'll hopefully have time to talk about later. So as it turns out, if you just sort of greedily aggregate on your blocks, then you get this runtime. So what do I mean by greedily aggregate? Every node at the bottom of my block just has some value. When 2 values sort of collide, we'll just apply our function to them. So here we have a 2 and a 3. We'll send those up. 3 gets sucked up by 2 because we're taking them in. And the only issue here now is like other parts are allowed to use these edges too, right? So we might keep trying to aggregate, but maybe this like annoying value 3 comes in from some other part. As it turns out, if you like break ties in a certain clever way, let's say we just forward 3 and then keep aggregating, you can show this round complexity. I don't want to talk about how we're breaking ties because it's not important. Really just what to note here is like that this algorithm gives you this round complexity. Okay, so now that we've aggregated at the root of the block, I guess also just notice that redistributing the value is just like doing the aggregation in reverse. So in particular, in this example, redistributing the value just looks something like this. Okay, so that we pick up a multiplicative 2 there. So that's fine, because big O. Okay, so now that we know how to aggregate on blocks, remember that we're actually trying to solve partwise aggregations. So we're trying to aggregate not across just a single block, but across the entire part. So the next point is that you can solve partwise aggregation in times B times D plus C, given that you already have these shortcuts. So the way this is going to work is we're just going to basically call this algorithm b times. Here's my proof sketch of this lemma right here. We're just going to do the following. We're going to first aggregate in blocks, and then we're going to allow nodes to trade with their neighbors in the part, and we're just going to repeat this b times. Okay? So if this is my part, and I'm trying to aggregate, so I'm trying to have everyone learn this one, the true value is 1, I'll do the following. First, I'll aggregate in blocks. So that'll look like this. Every node will trade with its neighbors in the part. So these are like these intra-part edges here. So we trade with neighbors in the part. They aggregate down based on what they heard. We aggregate in our blocks again. We trade with neighbors. We aggregate. And notice that like this true minimum value 1, every time we run the algorithm corresponding to this lemma is sort of like making one block further of progress. And then at the very end, we aggregate in our blocks. So this is going to take b times d plus c rounds, just because running this algorithm takes d plus c. And every part has at most b total blocks. That's like the definition of what b is. So if we and each time we run this and then trade with neighbors, we sort of spread our information one block further. So after repeating this b times, we'll have spread our information to every block in our part. OK. So like, cool. Like, we know that we could solve partwise aggregation if we like had a shortcut that had really good parameters b and c. OK? So this might not be useful. Like, maybe there aren't any good shortcuts. There's no good ways to like parameterize a shortcut. And you might not even be able to compute these things. So like, why would we care? The first lemma that I'm not going to prove is just that every shortcut admits, or every graph admits a shortcut with good parameters. So you can basically always get the block to be 1 and the congestion to be about root n. And this is like actually a really cute like 3 or 4 line proof. If any of you are curious about this, ask me afterwards. I'm going to skip this though. So and I guess the other point here is that these parameters for certain special families of graphs, like planar graphs, can be improved. And that's actually where our better results for like planar graphs come from. And genus-bounded and all those other special graphs. OK, so we also need to show that we can actually compute these things. As it turns out, you can compute these things where B star and C star are like the best block parameter and congestion admitted by a graph. I don't really want to talk about what that means, but you can basically compute the shortcut in the same amount of time that we use to actually solve partwise aggregation. So like all these things together tell us that we just solve partwise aggregation in basically d plus root n rounds. Why? Well, we know every graph admits a good shortcut. We know we can compute shortcuts that are competitive with the best shortcut that the graph admits. And we know given like a good shortcut, we can actually solve partwise aggregation. So all we have to do is just like run this algorithm to compute our shortcut. It'll compute a shortcut that has basically these parameters. And then we just run that lemma to solve partwise aggregation. So that's like a very brief sketch of like how you might actually use shortcuts to solve partwise aggregation and how you can get a round complexity of root n plus d. Does anyone have any questions about that? Yeah. Are these all? Yeah. So this is actually like previous work. This is mostly, I guess, stuff that Jason has done, or sorry, Goran has done, and also Jason has worked in this space. But yeah, this is like previous work. So we're just now going to get to like how you might make these message efficient, and like why this is not message efficient. We're basically like out of time at this point. This is my speaking skills talk, so I'm going to kind of just keep talking. But if you have to go, feel free to leave. I'll let like people who need to go like step out now, I guess. So it's like not too disruptive during the rest of the talk. I'll hopefully be able to like say everything else I need to say in like 10-ish, maybe 15 minutes. And you're fine to stay. And you had something at 1:30, you said? No problem. OK. Nathan, are you? OK. Yeah, I should be done by 1:30. This seems like a good stopping point. OK, cool. So like, the next question is, well, we've solved our problem with optimal round complexity. What can we say about the message complexity of our solutions for this thing? Like if it turned out that this also was getting optimal message complexities, we'd be very happy. Like we'd be done. We have our simultaneously optimal round message complexity algorithm. But as it turns out, this is not going to have good message complexity. So if you think back to how we were aggregating on blocks, and that's why I sketched this lemma, all we were doing was sort of greedily aggregating up these, the subtree corresponding to the block. Okay? So it's not very hard to actually construct an example where doing this is going to cost you a lot of messages. And here's such an example. So suppose we have d parts. So here are my d parts. And in each of these parts, we have about n over d nodes. Okay? So the thing to notice about this example, oh, sorry, all of the horizontal edges, this is a grid graph. All of the horizontal edges here are intra-part edges, so they connect nodes in a part. Each part is really just a path. And then all the vertical edges are like shortcut edges that all of these parts are allowed to use. Okay? So these are all like sort of in the same block, and like the root of that block is up there. Okay? So notice that like any one value in any particular part is not going to get aggregated with anything until it's gotten all the way to the root, because we're just going to keep sending each of these values up, and we only aggregate things that come from the same part. Okay? So what does aggregation looks like? We send up, we send up, we send up. So the thing to notice here is that every single value in this graph, when we greedily aggregate on this tree, is going to travel d hops, because we have d parts that they have to travel through, on average at least. So every value travels d hops, and a value traveling d hops is responsible uniquely for d messages, just because like traveling d hops means that like d nodes had to send a message once each. So the other thing to notice is that our network just has order n nodes. We have like, it's an order d by order n over d grid graph. So we just have d times n over d nodes, which is n. And each of these nodes uniquely corresponds to some value. So in total, the message complexity of this is going to be something like n times d. Okay? So again, we're shooting for like a message complexity of m. If d is super constant or something large, we're kind of hosed here. Okay. So now, if you stare at this particular example for a second, you might say, like, well, it's kind of silly for me to let every single node use my shortcut edges, because every time a node wants to like greedily aggregate on the tree, it's going to send a message all the way up my shortcut and cost me a bunch of messages. But I sort of have all these nice like intra-part edges that I'm not using at all. So the idea here is that maybe if we do some sort of local computation first, and then we aggregate down to just a single node in each part, or not a single node, just a few nodes in each part, and we only allow those parts, or those nodes, to use our shortcut to like finish off the aggregation of that part. Maybe we can reduce our message complexity. Okay? So this is going to, I'm just going to kind of briefly sketch the idea for how you might improve the message complexity of this particular counterexample. Actually turning that into like a full-fledged algorithm is like much of our paper, and I'm not really going to have time to get into too much of that. But this at least sketches some of like the general proof ideas. So what do? Well, we're going to take every one of our parts. We're just going to divide it up into so-called subparts, where each of these subparts has about d nodes. Okay? So here we have 6 subparts, this one, this one, this one, this one, that one, and that one. And each of these subparts has like d nodes, which means it has a diameter of about d. Now in each of these subparts, we're just going to like designate some node to be like the special representative for that subpart. And that special representative is the node that's going to be allowed to use our shortcut. Okay? So all we're going to do is we're going to sort of, within each subpart, aggregate to that special representative. Like he'll aggregate everything in his subpart, and then he alone is going to use the shortcut to finish off our aggregation of the part. So for this particular example, what this looks like is we'll have every node on the far right first send its value left, and then the middle node will aggregate what it gets from the node on the right with its own value. Then the middle nodes will send their value left. And now that we sort of aggregate down in our subparts, we'll then use our shortcut edges to like finish off our aggregation, like we were doing before. But notice that now we have many fewer messages actually traveling up our shortcut, or we have many fewer values traveling up our shortcut edges, so we have many fewer messages when we do this. So let's just quickly think about the rounded message complexity here. Oh, and I guess redistributing the result is, again, just symmetric to how you aggregate at the root. OK. So aggregating each of these subparts is going to take d rounds, just because we're aggregating down one more value each time we send something left. And each of these subparts is of size about d, just by definition. And again, keep in mind, I guess this is just a fix for this one counterexample. This is not like a general algorithm. Oops. So moreover, we're only using every edge in any subpart once when we send a value over it. Like we use this edge once to send this value there, and that one once to send those two aggregated values there. So we're going to definitely use every edge at most once. So we're going to have a message complexity of m. But like now let's think about what using our shortcuts cost us. So like before, this block is just a subtree of diameter d. So it takes us d rounds to send everything all the way up it. So nothing's changed there. But suddenly our message complexity is much better. Like we have n over d subparts, just because every subpart is of size d. And each of those subparts now has a representative that's responsible for sending something all the way up the subtree. So in total, our message complexity now is going to be something more like n over d times d, which is n. So like somehow we've magically reduced our message complexity down to something linear in n, which is like great for us. So combining these two lemmas, I guess the point is that you can aggregate on this particular block in d rounds with m messages. Okay? So this is like very much not an actual algorithm. I'm not touching on like a lot of the technical details here. So things I didn't talk about at all is like, well, I didn't talk about how you can compute shortcuts. I definitely didn't talk about how you can compute shortcuts in a message efficient manner. In this example, we assumed that every node sort of knew the topology of the graph and it divided up nicely into subparts. But we actually have to somehow divide up our parts into subparts in a way that's both message and round efficient. This is just a solution for combining in a single block. We have to combine in a whole part, not just blocks in that part. And we can't just kind of port our solution, or we can't just use the previous solution, which like aggregated in blocks and then traded with neighbors, then aggregated in blocks and then traded with neighbors, because as it turns out, that's not message efficient, so you need to do some more work there. And lastly, we do all these things deterministically. And like a lot of the meat of our technical work goes into like how can you de-randomize algorithms to do these sorts of things. Like if you think about it, computing subparts with randomization isn't that hard because we can sort of just randomly sample representatives and they'll sort of claim balls around them. But if you want to do that deterministically, you have to think a lot harder. Okay, and there are some other like technical details I don't even really have time to mention. But so I want to just like leave you all with a quick summary of my talk. I guess the main takeaway is just that in the congest setting, at least, you can give algorithms that simultaneously optimize with respect to both rounds and messages. These are examples of such algorithms. We get all of these results from solving this primitive partwise aggregation. And the main sort of techniques that I touch upon are these ideas of shortcuts, where the idea here is just if you have some part and you want nodes to communicate within that part efficiently, allowing them to use edges outside of the part can speed up communication. And I like briefly touch on this idea of like dividing up parts into subparts and sort of locally doing things before you like use shortcuts to reduce message complexity. So thank you all. Questions for me? What are the open problems? I guess like one active area of research is how can we improve, well, for like things beyond like planar, treewidth, genus-bounded, and all of those, what other families of graphs that make good shortcuts? So I know like Jason and Goran and Bernard are like working on like what sort of shortcuts do minor-free graphs admit. I mean, as far as these particular problems are concerned, it's kind of like a closed book because we have two like metrics that we're interested in optimizing, and we optimize both of them with a single algorithm. I suppose you could always like try and shave log factors. The logs that are being hidden by these tildes are like pretty beefy logs. Yeah, I guess that would be my response to open questions. Yeah.
So are these approximation factors? These like 1 plus epsilon, or are these like 500?
So the shortest path one here is like an approximation factor in the length of the longest path between any two vertices or something like that. the min cut is a good approximation. I don't know it off the top of my head.
So they're not, like, it's not a constant for shortest path?
No, no. Or Jason would know better. So really, we just improved this primitive. Other papers have used this primitive before to solve these problems, so I'm not like super familiar with how these work. Jason is actually the point man for the shortest paths approximation, so he might be able to tell you. But yeah, Greg.
Are there any restrictions on which functions you can do this pairwise aggregation for? Because it seems like even though you have unbounded computation, like
Yeah.
you have this limited communication property. So.
Yeah, so I mean, it's certainly, the question is like, what sort of limitations do you have on the function for pairwise aggregation? It's definitely the case that, well, the limitations we impose on it, it's not clear that these are strictly necessary, but probably they are, is that it's like commutative because you can't really dictate in what order do values get combined. And like I said before, that like its inputs are of size log n and its outputs are of size log n. I guess any sort of, I mean, the trivial thing you can always do is if like my inputs are of size, I don't know, log squared n, I can always like operate in like meta rounds, each of size log n, to transmit these bigger values. I don't know that that's an interesting or useful solution, but any more questions? Paul?
In particular, if I remember correctly, you, the way you described it, you could put the same value multiple times in the function. Is that something that you actually need to do?
Yeah, so that's actually a great question. I purposefully kind of swept this under the rug. So the question is, like, it seems like what you can do is you can apply your function multiple times to a value without changing the output. So like, if we're doing min, for example, and I have like, you know, I've aggregated down to 5 and I've aggregated down to 5, but maybe like some of these two things are aggregations of the same stuff, I can always just apply min again. Really, this works for functions like, say, sum that don't satisfy this property. So if I have like, you know, a sum of 5 things and a sum of 5 things, but there's some overlap, I can't just like stick these two things together. So that's a technical detail that I purposefully hid, but actually like what we're doing works for these sorts of functions. Like really all we need is commutative. And like I guess the short answer for how you algorithmically get around this is you don't sort of like flood the network with things in the way that I've been giving as like a caricature of our work. So really you'll sort of like aggregate things up a tree, for instance, whatever that means. But any more questions? Was there? Oh yeah, Jason.
Do you know, are you familiar with the line of work where like you just bring down the number of edges from n to n?
Yeah. Okay. So there's Jason asked about like this line of work where you can bring down the message complexity from n to n. So there's who is this? King, I think Valerie King. Yeah. Yeah. So basically, this message lower bound of m, which has like been known for several decades, doesn't hold if you make certain like strange changes in assumptions about the CONGEST model that you're working in. So there's sort of questions about like, what does a node really know right when it wakes up? Like, does it know the ID of its neighbors? Does it only strictly know its own ID? And actually, if like a node knows the IDs of its neighbors and your algorithm is allowed to be randomized, this lower bound doesn't hold. It's kind of folklore of the community at this point that it's just m, like, who cares? But there is like a line of work that's interested in like breaking that lower bound by making slight tweaks to the model. Any other questions?
You suspect that's going to be the much improved for this work?
That's a good question. A lot of the stuff we do, I mean, at least to me, it's not clear at all how you could get it below m. And I'm not totally sure how like the algorithms in that line of work really work. But yeah, it's possible though.